Oops, I got my little ahead of myself here. So let me just make this obvious. This is the answer to this part, sorry. Although, I mean, it's related. But you'd have 25 vertical marks on the graph. And about 23 to 24 of them should have the true population proportion within their limits. And my husband's coming in the door. Let's see if I can pause it. Okay, he's in. Now, so you'd have a whole bunch of vertical marks, not just 3, but you'd have 25 of them. And roughly 95% of them would contain this red line, which is what it really was. Okay? And that would mean that, 1 to 2 students would probably not have it. I mean, if you took random samples in the class. Alrighty, cool. Now the question becomes, how the heck do you make those marks? Where in the world did I get 7.7 from, or 8.3 from, and all that? And the answer is this formula. Ta-da! There it is. All right. So when working with proportions, we're really working with the binomial distribution. Right. Now you can see that in this formula up here. So for example, that n times p times 1 minus p thing, that was one of the last things we covered in chapter 6.2. Right? The n being less than or equal to 0.05, that's because we need independence, right? And if you have less than 5% of your population, then you're ensuring that you're not oversampling to the point where people are going to start calling each other and saying, hey, they're questioning me about the economy again, right? And this right up here is the formula for the standard deviation, right? According to section 8.2, standard deviation of the sampling distribution of the sample proportion, 8.2. So all of this is based off of the binomial distribution. So n times p times 1 minus p here. N times p times 1 minus p greater than 10 shows that the binomial distribution is approximately normal, which is good. You need normal because normal is where we're going to get that z-score thing from. N less than or equal to 0.05, capital N ensures that the samples are independent, which you remember from sections 6.2 is kind of a big deal, right? And let's just think about this. I mean, when they call you up, you have success, right, which would be agree with their position or something like that, or, yay, I'm going to vote for candidate X or whatever. And then you have failure, which is do not agree, will not vote for X, etc. Okay? So you have success and you have failure. 2 options, right? It's really truly binomial, which is why I stressed 6.2 and 8.2 so much, because 6.2 and 8.2 are what laid the foundations for these formulas right here. All right, note that at the bottom of the box it says that is stated. How does this ensure the binomial? Oh, I just wrote that right here. Let's put it down here. I didn't even see where I was going. And we learned that this is actually the value equivalent. I already said all this. It's like I planned it or something. Sigma p hat. Which is the standard deviation of sample means. Or sample proportions, I'm sorry. How much did this proportions vary from sample to sample? So for example, let's say you're running up to a presidential election, you poll them one week, what percentage are going to vote for candidate X? Then you do it again next week, what percentage are going to vote for candidate X? And again, and again, and again. How did the weeks vary from each other? That's what this measures. This tells you how weeks varied from week 1 to week 2 to week 3. Variability. All right, then we learned that, oops, I already wrote that. Man, it's like I totally planned it. So down here, n times p times 1 minus p shows that it's approximately normal. Go look at the last section of 6.2 and you'll see that's what we talked about. You need normal, you need it to have a standard deviation, you need them to be independent, and you need either success or failure to make all this work.